Hello and welcome. In this video, we're going to review how you can run experiments in Pybamm. Now, if you're not familiar first with running simulations in Pybamm, we highly recommend that you check out the earlier lecture, A Basic Introduction to Pybamm. Then when you're ready, go ahead and return to this lecture video. Now, let's get started. What is an experiment? In Pybamm, the experiment is a class that contains a useful mechanism for preparing battery model simulations under specific operating conditions. Users can prepare an experiment in Pybamm by passing a human-readable series of instructions as a list of string entries to the Pybamm.experiment class. For example, if I want to set up an experiment to run a 1C discharge until my battery's voltage reaches 2.8 volts, and then give it some small portion of rest, I could do that with the code shown below. So we set a variable to experiment, call the Pybamm.experiment class, and pass in our list of two string entries, really a tuple. First one, we're discharging at 1C until 2.8 volts, and then the second one, we're resting the battery, meaning that there's no current being applied for a period of 10 minutes. Now, it's important to mention, you're not just limited to C rate or time-based specifications. We can also pass instructions to run the model under load conditions or until a specific voltage condition has been achieved. For example, if we wanted, we can even include a constant voltage hold condition where we taper the current to maintain the battery's voltage at some maximum or minimum operating condition. This is pretty common when we're topping off a battery to achieve a full state of charge condition, where we've got a previous C rate that's applied as we're reaching, some specific region before 90% state of charge or 80% or whatever it is. And then as we get closer to 100%, we taper the current and back it off, hit our maximum operating voltage for the battery, and then we just keep the voltage constant and taper the current to get in that residual energy into the battery. Now, we can also change instructions in our experiment from a C rate basis to a specific current. And we're not limited to monotonic scenarios such as strict charge or discharge scenarios like we showed in the above example. Let's go through our first execution of a Pybamm experiment with an example simulating these conditions. And we're going to go through in this video 5 examples. So first, our simple monotonic experiment. I'm going to get started by loading our virtual environment and the required packages. So I'm going to start importing matplotlib for plotting, NumPy, and then Pybamm. Okay? And I'm loading my virtual environment. Obviously, if you don't have one, not a problem, nothing to worry about. Now, once that's imported, we're going to load our model, specify the battery that we have, and set up our simulation within its operating conditions. So I'm going to load my model. For this example, we're going to go through with an SPME, and then I'm going to take the chemistry from the Chen 2020 paper for parameter sets. I'm going to set the parameter values by calling pybamm.parameterValues, setting values equal to chemistry. Now, it's important to note I am using the Pybamm version 24.1. So if you're using an older version, you might actually have to specify chemistry is equal to, and then your variable instead of values. So just keep that in mind. Then, once I've got that set, all we need to do is to set our experiment. So again, I'm setting my variable to the name experiment. We're calling our Pybamm.experiment class and passing in a list of entries. So we're going to discharge at a C over 3 or a 0.3 C rate until 3.7 volts. Then we're going to charge at a 0.3 C rate until 4.2 volts. Let's hold that at 4.2 volts until 50 milliamps. So in this condition, we're going to, again, taper that current until we hit 50 milliamps as our current condition. Once it's there, we're going to rest for 5 minutes and then apply a discharge at 1C until 3.5 volts. And there we're going to hold at 3.5 volts until C over 10. So this is the experiment that I have set up. We're going to call it by setting our simulation variable. We're going to call pybamm.simulation. Pass in our model that we've defined, so our single particle model with electrolyte, specifying our experiment conditions and the parameter values that specify our battery. Then we're going to call our sim.solve, and then after that, we're going to plot our results. Okay, so while this is running, so we see it just finished, Before we plot this out, just review what we did, right? So we passed in a list of string tuples that read like a simple instruction guide. The Pybamm developers created the experiment class in such a way that it's similar to reading a standard operating procedure document that you might be familiar with if you had to execute this as a physical test in a lab environment. This helps ensure the model developer that test conditions specified in the model reflect your intended test procedure. So with that, let's go ahead and look at our results. And keep in mind, the intent here is we should see discharge, charge, some current tapering, and some period of rest where the current is 0. So calling the simulation.plot, you can see, looking on the far right, our current versus time and our voltage versus time profile. Pretty clearly, you can see here that we are discharging, and then we are hitting our charge condition. And as you notice, the current gets this little arc. That's where we're hitting our CV taper, where we have a constant voltage, and we're going to taper the current as we approach that specific voltage condition. We then apply a rest, so the current is backs off, and then we discharge the battery. Okay, so in our experiment, you can see how we're changing according to different C rate conditions. In the voltage versus time, you can see the constant voltage hold, and also keep in mind that we're demonstrating this example with an SVME model. So while this was pretty fast using the simulation, if you're running a Doyle-Fuller-Newman model or another model that has additional complexity, it's going to be more time intensive. So depending on the instructions you're passing, the duration of your experiment, and the model complexity, that's all going to impact how long it's going to take you to solve your model. Also, I should mention, if you look in Pybamm, when we look at our plot results, you have this dynamic widget. So if you want to look at and see a specific instance in time, you can just scroll onto that condition and the plots will update. So what's unique here is if you look on some of these other plots, voltage and current obviously are versus time. So those are just going to call out that specific instance where you're at. But you can also look at how the electrolyte concentration is changing as a function of time during this test, or how the electrolyte potential is changing. Now, moving onward, let's go to our next example, running an experiment with many repeated test conditions. So we saw in the above part that you can run many charge and discharge protocols, but how can we manage a test that has a lot of repetition, or at least do so in a way that's not super coding intensive, and also in a way that is manageable for Pybamm? So to explore how we can set this up, we're going to base our example on the test that Cho, Lee, and Kim used to get data to fit their equivalent circuit model. So we're going to take a series of charge-discharge profiles followed by an HPPC pulse characterization profile. Now in this, they first charged and discharged the cell between 4.2 and 2.5 volts, and they used a 0.5 C rate, or C over 2. And they did apply some level of current taper, though it's not specified in the paper, so we're going to just put a ballpark guess there. And then they allowed the battery to rest for 1 hour between conditions. Once that was finished, they then charged the cell up to 95% state of charge with the 0.5 C rate, and then applied a pulse profile at every 5% SOC increment. Those pulses aren't exactly specified either, so we're going to put in some generic guesses there. But we can see that there's a discharge pulse followed by a charge pulse, and then we discharge the battery to the next 5% SOC window, so going from 95% to 90%. With that, we're going to just make some base assumptions here. So let's just have the battery discharge or charge for 18 seconds. We're going to rest for 1 minute between the pulses, and then as we are discharging, we're going to go through this process and repeat it each time for 5% SOC. So you could see in the previous tuple callout, this could get pretty, tedious, because we're going to say, hey, discharge, rest, charge, rest, couple more steps, and then rinse and repeat, and we'd have to do this 19 times between 5% and 95% for a 5% increment. So, we want to avoid doing that. Now, unfortunately, in the current version of Pybamm 24.1, it doesn't allow for SOC-based steps aside from the experiment termination condition. So we can either set up the experiment in Pybamm by breaking it up into 19 different experiments, which you could do. There's nothing wrong with that. Or another way you could do this is by passing one long experiment where we relate the SOC condition to its open circuit voltage of the cell at the given SOC. So, relating, we know at a given state of charge, if the battery is fully at rest, then the open circuit voltage should be a specific value. Now, we're going to go through and do that. And so let's demonstrate how you can do this in a single experiment with the voltage declared. Now, keep in mind, if I knew the cell's operating or open circuit voltage at each 5% SOC increment from test data, then I would just directly provide that value. However, I don't have that on hand, so we're going to actually use Pybamm's experiment method to pull out what is a simulation prediction of the OCV. And so the way that I'm going to do this is just pass in a Pybamm experiment where we're not doing anything to the battery. We're just going to rest it for some arbitrary amount of time and then discharge it. And I'm just going to pull out that very first voltage value. And because what I'm going to do is specify what the initial SOC is in the model. So the way that we're going to do this is we're going to set up our simulation. So we've got our model, we have our experiment, which is set to the simple rest and then discharge. Parameter values, nothing is new there. But next, what's going to happen is I'm going to create an empty list of OCV values, and I'm going to pass in my list of state of charge values. I'm going to loop through this model experiment, and for each one, I'm going to call the simulation solve method so that we solve at each state of charge. So for each state of charge, from 95% to 5%, we're going to figure out what that open circuit voltage looks like. And then I'm going to append that to my OCV vals list. So let's go ahead and run this. And we're going to just print this out at the very bottom to see, we should have a list of about 19 open circuit voltage values. I'm going to go ahead and pause the video and we'll resume. Okay, so now we've got our list of 19 open circuit voltage values. And you can see from 95% to 5% that ranges from 4.12 volts to 3.1 volts for this specific battery. Now, before we feed all that into an experiment, let's set up our duplicated step. So we know that for each pulse, after the first one at 95%, that they're all going to discharge for 5%, they're going to rest for 1 hour, pulse for discharge for a period of time, rest for a minute, do their charge pulse, rest for a minute, and then move on to the next condition. We're going to use list comprehension to iterate through our OCV list and set this up. So I'm going to pass my instructions as this list. So we're going to say, again, the discharge at the half C rate until, and then I'm calling, this value, so the SOC, that's going to be called, and I'm just rounding it, right, to the second decimal place. We're going to rest for 60 minutes, discharge at a half C rate for 18 seconds. This is our discharge pulse. Rest for a minute, and then charge for a half C rate for 18 seconds, and then rest. Using list comprehension, so you see how I've got value there specified instead of SOC0 or SOCI. So this is just so I can say for SOC in, or for value in OCV values. Okay, so this is how I'm passing in the voltage value. And so let's go ahead and just create that. And what I should get is this list of basically the 18 repeated conditions, right, for each one. And so you can see we've got a series of these tuple entries going from our 4.1 ballpark to 3.1 volt condition. Now, all that we need to do is just append and add this, or add our beginning conditions, which is that we're going to start with a C/2 charge to 4.2 volts, then discharge to 2.5 volts, right? And then charge it right back up to the 95% condition. So I'm going to specify that here. So we're charging, we've got our hold condition, we're going to discharge, hold for an hour as well, and then charge it right back to the 95% state of charge. run a rest for a period of time, and then because, unique in this condition, we didn't add our first OCV point, I'm going to specify the pulses explicitly here. Now, the way that we can insert this at the very beginning is using the insert method. So, I'm just calling to my instructions list, insert. I'm inserting that at the very beginning, our beginning of experiment condition. So now if I run that, my new instructions, you'll see that now we're starting with our condition to do the C/2 cycle between 4.2 and 2.5 volts. Okay, so now that we've got that set up, all we have to do is set up our simulation, run the model. So we're going to pass in our instructions, no change to our parameter values, and then just hit sim.solve and sim.plot. Excellent. So now we've got our results, and here's what's really cool. You can see on our current versus time and our voltage versus time profile that we have a series of charge discharge occurring, and then that staircase that you can see from our 5% increment, where we are changing across the SOC spectrum over time. We are running a pulse, discharging on another pulse, and then staircase change to the next SOC. And so, this is pretty common. As I mentioned in the paper, they use this so that they could pull out time constants for building an equivalent circuit model. So this is a pretty common test that you might see. And just an exciting way that we can see Pybamm can fairly quickly set this up and take a series of fairly complex steps and build a model and run predictions off of it. As always, you can run through the widget and see how the test is changing over time. Now let's move on to our fourth experiment, and that's going to be experiments with temperature conditions. So in the experiment above, we didn't specify unique operating temperature. And you really need to be mindful of this while working in Pybamm experiments, because if the temperature is not specified in the experiment, then we're going to default to what is specified in the parameter values for our loaded model. And likewise, if you're not specifying a thermal package, in other words, you're not saying, hey, I'm including some thermal modeling here, then it's going to default as an isothermal experiment. Now we can view what the model temperature is by accessing our parameter values dictionary. And so I'm going to do that by just printing out our parameter values, and the key that I'm calling is the initial temperature, right? In Pybamm for the initial temperature the cell or battery is operating at, the ambient temperature for the surrounding environment, and then the reference temperature at which the parameter values were identified for the battery. So we can see for this specific paper and this specific battery model that they were all set to 298 Kelvin, a pretty standard operating condition. If we want to plot the temperature versus experiment, you'll notice that we didn't specify the dynamic temperature profile. And so again, since we didn't load a thermal model, then we're just going to get a flat line across the board. And we can see that by calling the sim.solution entries, extracting our cell temperature and our time. So I'm going to have time as my x-axis, cell temperature as my y, and then just plotting that in matplotlib. So as you see, no thermal model loaded, flat line. Now let's say that we want to update our initialization temperatures. Let's say I'm not running at 298, I'm running at 35, 40, 55, another temperature, Celsius. So in that case, I'm going to update in Kelvin here the parameter values for initial temperature or ambient temperature. Same thing, you could apply for reference temperature as well, but we're just declaring the new condition here, setting it to 310 or 305, what have you, and then running our simulation. I mentioned that you need to rerun the simulation, of course, because you are fundamentally changing the parameter value that's an input to it. So this is how you have to adjust the temperature. Okay, so now let's move on to example number 4, where you're running an experiment with non-isothermal conditions. To modify our test so it's no longer isothermal, we're going to update our model options and add the thermal condition. If you want to check out a list of thermal model options depending on your battery cell type, you can check out Pybamm's documentations. I've included a link in this Jupyter Notebook file. But it's important to recognize the thermal implications that can really influence the practical limitations of your battery. So for example, if you're having a really resistive performance and getting a lot of heat being generated, you might start to approach a thermal limit where your battery can't operate. Or likewise, if the battery is in a really frigid chamber, but you're running in this high strenuous scenario, maybe the battery is actually heating up. And as we know, at higher temperatures, when it might be more capable than at low temperatures. So, something to consider. If we want to declare a non-isothermal model, what we're first going to do is set up an option, and I'm going to pass in a dictionary and just calling the lumped thermal model. So there are other types, but thermal model or a lumped thermal model is pretty common, and for this case, I think it works well. I'm just going to specify then in my model that the options I'm going to load in, these specific model types, I'm going to load in the thermal model, lumped thermal model option. Then in the simulation, we're going to go through the same experiment that we looked at before, that pulse profile that we were modifying and adjusting through. And keeping the same parameter values, so at 298 Kelvin, and then we're going to hit solve. I've added some code here from what you saw before, where we're going to pull out the temperature versus time, and then we just want to plot that and see what that looks like on the board. So let's go ahead and run this. Okay, so it looks like our model has finished. So this is our temperature versus time. So remember how in the this is our HPPC plus the C/2 cycle charge discharge profile. And previously we had it as isothermal, right? Just a flat line. But you can notice how even in a simple lumped model that the temperature rises, right, and is pretty or heavily impacted by the condition that you're operating the battery under. So we can see, for example, while we're charging, this steady and steep rise in temperature. It's going to sharp, drop as we are beginning to rest the battery, and it's going to cool down. And then it seems like at each pulse that we're going to get this change in temperature, and it's not consistent, right? The amount of temperature change is variable based on which state of charge you're at. In other words, you could say that at different states of charge, the battery is more resistive and that there is a greater level of heat generation that the battery is experiencing at these different conditions. So let's go ahead and just compare the model's voltage versus time. I think that could be another interesting example. This will be pretty quick because we've already got the model simulation results. So I'm just going to call that by pulling out the voltage entries and the time entries and plotting that. Okay, so as you can see here, right, we're going through starting at our 4.2 volt condition, and you see that same taper cliff. And as we're getting to those lower states of charge, we see the spikes, at least for the pulses, having these higher levels of temperature associated with those greater resistances. So pretty exciting, kind of cool to see. So let's summarize in this lecture. So we've gone through 5 different experiments. We've looked at how the Pybamm experiment class can be used in Python using a simple monotonic profile. We've looked at using different load profiles, including current tapers for voltage hold conditions. We've also looked at complicated profiles using dynamic tests like HPPC profiling, and how we can use list comprehension to really streamline running that and just preventing repetition code lines from being written manually. After that, we also looked at how to add temperature conditions in our tests and how to specify our thermal model so that we can run and look at temperature changes and how that might impact our results. Now, in the next lecture, we're going to cover how you can feed test data into an example. As you can imagine, it's really interesting to be able to simulate a battery's performance, but oftentimes what we want to do as a sense check is make sure that our model is predicting and performing well relative to test data that we might have for the battery. So we're going to cover that in our next lecture. But that's all we have for today. I hope you enjoyed this training. Thanks. Hey, thank you so much for checking out this video. I really hope you've enjoyed learning how to run experiments in Pybamm. If you want to check out more of our videos or see more content related to battery modeling or battery data analysis, go ahead and subscribe to my channel. Thanks so much, and I look forward to seeing you soon. Bye for now.